Good afternoon. Welcome to Krishna's class. In this talk, we consider another Hahn-Banach theorem, namely the Hahn-Banach separation theorem. It's a very fascinating result, and it's quite easy to understand what it is. Suppose you take R2. In R2, suppose you have two regions which are disjoint and convex. So the properties are, let us take this convex, but they are disjoint. Then what the theorem says is the following. There exists a hyperplane which separates the two regions. So this is the hyperplane. What is a hyperplane? Hyperplane is a hyperspace translated. Okay, it's a translation of a hyperspace. What's a hyperspace? Hyperspace is a subspace of R2. In this case, it's a line. So it's any straight line passing through. And with the property that this particular hyperplane does not intersect either of these regions. Okay, so this is the idea. We have two convex regions. Convexity is important. Then there exists a hyperplane, which is a line, which is a straight line in R2, which separates the two regions, namely, it does not intersect either of them. Okay. Now, suppose you drop convexity. Suppose you take a region like this. These two regions. Because one of them is nearly convex, the other one is not. Does there exist a, so call this E1 and E2, does there exist a straight line which separates the two regions? The answer is no. Because any straight line that you take, if you avoid one region, it will certainly intersect. Okay. Therefore, you see that the convexity is what is not there. So we will see that this theorem has a more abstract manifestation in Banach spaces. This is the Hahn-Banach separation theorem. So the Hahn-Banach separation theorem is this: if E1 and E2 are two convex subsets of R2, then there exists a line which separates E1 and provided E1 intersection E2 is not. So let us work it out. This is the Hahn-Banach separation theorem. Prove this. We will first give the statement. Statement of the theorem. Let X be a non-linear space over K. K stands for either R or C. Let E2 be non-empty disjoint convex subsets of X, convex subsets of X, where E1 is so we have two non-empty disjoint convex subsets of X where E1 is assumed to be open. One of them is assumed to be open. Then there exists a real hyperplane in X and E2, E1 and E2, in the sense that for F belonging to the dual space X star or X prime the space of all continuous linear functions. So now let me use the previous notation X star and T belonging to R. We have real part of is less than T X2 for every X1 and X2. For every X1 belonging to E1 and X2 belonging to E2. This is the theorem. It simply says that there is a hyperplane that separates the two sets E1 and E2. Okay. So I will explain this out. So we are talking about a real linear function. Now suppose you have a complex linear function, then the real part of it is a real linear function. We have earlier considered this case. So we need some supporting results to prove this theorem. So let me write down. We shall not move now. I recommend to refer to functional analysis by Kumar. So the first supporting result that it is, let X be normally union space. If E1 is open X and E2 is a subset of X, then E1 plus E2 Next, E1 plus E2 is the usual definition. Okay, so that is one result. So if you have an open set, you have some other subset, take the sum of the two, because sum is sensible here because you are working in a linear space. So there is addition well defined. So E1 plus L2 is well defined. E1 plus E2 is a subset which is a open subset. Okay, so that is one result. Second result that we shall use is non-linear space over K. E a non-empty open convex subset of X. Let Y be a subspace such that empty. Then there exists a bounded linear function such that fx equal to 0 y is a subspace, but real part of second result says that X is a non-linear space over K. K is R or C. E is a non-empty open convex subset of X. Now let Y be a subspace such that E intersection Y is empty. Then what happens? You have, there exists a F belonging to X star such that Fx equal to 0 for every X belonging to Y. But real part of Fx is not equal to 0 for every X belonging to E. Okay. Now, it's quite easy to see. See what this says is that, okay. In R2, let us again. So you have a E which is non-empty open convex subset of X. And let Y be a subspace. So any subspace is this. It's a line passing through the object. Y be a subspace such that E intersection Y is empty. This E and Y do not intersect. Then there exists a linear function f belonging to X star such that Fx equal to 0 for every X belonging to Y. Or in other words, the null space of the null space of F. The null space of F is contained in Y. Okay, null space of F is contained in Y, but real part of Fx is not equal to 0 for every x belonging. So you have, so actually you see that you recall the interpretation of a linear functional. So you have a linear functional, then this can be identified with a hyperspace, in the sense that you are taking the null space of that linear functional. It is going to be a hyperspace in the vector space. Okay, so you can identify the linear function with that, whose null space is equal to the hyperspace. Okay, and then for any E, any element outside, you can construct a linear function which is parallel to this. Sorry, a line which is parallel to this, or a hyperplane parallel to this. And you see that this does not take the value, it does not take the value anywhere. So you see that you have all kinds of lines parallel. But this is of the form some y plus alpha. So it's a some non-zero constant. Okay, so that's the interpretation of that. We shall go to the third result. It's a simple theorem. Normally linear space F star. If E is an open subset of X, then F of E, the image of E under F is an open subset of here. What you have is this. Is contained in K. Now suppose openness of this implies openness of this. This is the, we will use these three results somewhere in the proof of theorem. So let us now build the proof. Okay. Proof is very simple. Let non-empty disjoint convex sets and E is E1 is, this is the basic assumption. Okay, then what we can immediately infer is the following. Look at E1 minus. What is E1 minus E2? E1 minus E2 is set of all x1 minus x2 where collection of all x1 minus x2 where x1 belongs to E1 and x2 belongs to E2. Now we apply the supporting theorems to conclude the form. First supporting theorem apply, and we get the first theorem, E1 minus E2 is convex is non-empty. First of all, why it is non-empty? Because they are disjoint. Okay, so if you have an x, there is no other x minus x or x in the other one, so that their difference is 0. It's not there. So it is non-empty. And convex and convex, that is simple, and by 1 so you have this property E1 minus E2 is non-empty and convex, and by 1 again it is open. Okay. Also, zero is not in E1 minus, since it is empty. That's the reason for that. So let us take Y to be the zero subspace and E to be equal to E1 minus E2 into, make that choice. Then by 2 there exists f x star such that is not equal. So the typical element of E1 is x1 minus x2, where of course x1 belongs to E1 What does this mean? F of x1 minus x2 is f of x1 minus f of x2. Therefore, what you have is that real part of This is just using the fact that f is linear. What is the implication? The implication is that these subsets are disjoint. I mean, they are subsets of either the real line or the complex plane, but they are the subsets of the real line. Therefore, it implies understand. That's the conclusion there. Further, they are convex subsets of R. That's easy to prove because you see that E1 and E2 are convex. Therefore, you see that if you take a x1 and y1 belonging to E1, then you see that t x1 plus 1 minus t y1 belongs to E. So use that property. So this follows from the convexity of E1 and the linearity of therefore what do we get? Hence they are non because if you take 2 points in this set, what happens? That's the form f of x1 and f of y1. Okay. Now you know that the line joining x1 y1 is in E1 map with f. So you get all the any intermediary point on that set real f E1. You have a corresponding t such that t is equal to tx1 plus 1 minus t. Apply the linearity of real f. Get the result. So that's easy. So they are non-overlapping intervals. So we have proved that they are non-overlapping. They are also now intervals. Now we shall assume real lies to the left of f into, okay, without loss of generality. Why without loss of generality? That doesn't happen. It is going to be real part of f. E1 lies to the right of real part of f, E2. Now work with minus f. Work with minus f will go turn around. Okay, so there is no loss of generality in assuming this. So if f doesn't work, you work with minus f. So either for f or for minus f, this statement is true. Which is true for minus f. So there is no loss of generality. Now if you look at this real f from x to is a continuous real linear and E1 is a open set Now this is the assumption that E1 is an open set subset of X. Okay. So what can you conclude? Hence, by third theorem, we have is an open interval something of the form is so let me write this as a T. T is the right element of interval. If T is right of the interval, then we have real for x1 2. Now geometrically what this says is this. You consider the linear functional. Just examine the geometry. Explain. real hyperplane so set upon x belonging to x such that equal to t, which is a translator, and by the above inequality and E2 lies right of it. That is, you have E1 is contained in and so E1 and E2 are actually separated by the linear function f through the hyperplane it determines and passing through. So this is the theorem. Okay, as I have shown in a tutorial that if you drop the convexity, the result will not be right. Okay, thank you very much. So that completes our discussion on Banach spaces. There are many related results that you can see. You please refer to Functional Analysis by B.V. Limai. It's a beautiful book which gives you a lot of insight into the various results. Especially good geometric insight is given by that. Thank you very much.